and section 4.1. Okay. Chapter 4 deals with the application of differentiations. Okay. In this chapter, we will cover several applications of derivatives of a function, and these derivatives are very useful in getting some information about the shape of the graph of a function. Okay. And we will cover L'Hopital's rules and the way to find the optimal solutions of several practical problems which raised in our daily life, such as minimizing cost, a time, a distance, or maximizing an area or volume or a profit. Okay, those are all the applications of differentiation. First, section 4.1, extreme values of a function. Let f be a function defined on D, and this function f has an absolute value at C if f of C is always greater than or equal to f of x for all x in D. Okay, so this number, in this case, the number f of C is called the absolute maximum value of f on D. Absolute minimum at C can be defined in the similar value. That if f of C is less than or equal to f of x on all x's in D, okay, then this f of C is called the minimum value of f on D. Okay, then a function f is called to have a local maximum or relative maximum at C if f of C is greater than equal to f of x when x is near C, which means there exists some open interval I near C, containing C, such that f of C is always bigger than or equal to f of C for all x in intersection of D and I. Okay. Then this f of C is called the local maximum value of f on D. And local minimum at C is defined in a similar way. Okay. By the definition, the global maximum and global minimum values are local maximum and local minimum values of f respectively. Okay. However, the converse is not true in general. Okay. Converse is not true in general. In general, the local maximum and local minimum values are called the extreme values of a function. The local maximum and local minimums are called the extreme value, not global maximum and global minimum. This figure 1 shows what is discussed. Okay, so let's see. Here, this curve has a local minimum here, and local maximum here, and local minimum here, and local maximum here, and this is called the global maximum, and this it must be the absolute minimum or global minimum. This shows all the situations that we discussed. Okay. The first example is f of x is equal to cosine x. Since cosine x is in between 1 and minus 1 and minus 1 for all x, and cosine 2 and pi is equal to 1, this cosine function has many local maximum, which is actually the absolute and global maximum, which is 1. F has infinite many ones. The cosine x has infinite many maximums. And also, this cosine function has the minimum value of minus 1. infinite many times. So, those example shows, okay, the extreme value theorem. First theorem, we talk about the extreme theorem, expression. Because this shows some functions has extreme values wherever, whereas others do not. Because let's look at the example 2. F of x is equal to 1 of x, which is looks like this. I may write it here. Okay, this sine function, this f of x can be drawn in this way. Okay, so here, these lower values getting smaller and smaller, all the way to the plus infinity here. So there is no minimum, local minimum value. This x, f of x value goes all the way to the infinity. So there is no local maximum. Eventually, so there is no global maximum as well neither. So this f of x has no extreme values. So we need to know when a function has the extreme values. Okay, when does not. So this first theorem, the extreme value theorem, tells about it. If this the function f is continuous, if the function f is continuous on a closed interval, it should be continuous. It should be continuous and on a closed interval ab. Then f always attain an absolute maximum value and absolute minimum value at some number c and d in the closed interval. Okay, so here the both hypotheses, continuity and closed intervals, are very important. Here is the examples. This is the function which does not have a local maximum because it is not continuous. So the theorem 1 doesn't work. Doesn't work for this function. This function is continuous, but the domain is not closed. Here is the open interval. This is even though this is closed. So the domain is not closed. So even if the function is continuous, it still does not have a local minimum, the relative minimum and global minimum, absolute minimum. There is no one. So the two conditions of extreme value theorems are both very important. Continuous on a closed interval. Okay, let us now consider extreme values for differential functions. Okay, differential functions. In figure 1, and then we had the tangent lines, horizontal tangent line at 4 points C1, C2, C3, and C4. Okay, it suggests f has a local maximum or minimum at those extreme values. Okay, here we know this the f prime of C1, 2, 3, 4 are all 0 because the tangent line were all horizontal lines. Okay, with this observation, we can draw the second theorem, Fermat's theorem. If f is differentiable at x is equal to c and has an extreme value as c, then f prime of c must be 0. Okay, it's a differentiable and it has extreme value as c. Then f prime of c should be 0. Okay, okay, you have to fill out the proof as an exercise 28 at the end. But the converse of this theorem is not always true. Okay, because look at this example. F of x is equal to x cubed. Then the graph of this can be drawn in this way. Okay, in here, the f prime of 0, f prime of 0 here, at the origins are 0, but it has no extreme value at c is equal to 0. Here, there is no local maximum or local minimum, either local maximum or minimum at the origin. Okay? Because what? Because what? Because this says, this Fermat's theorem, the converse of Fermat's theorem does not work, even though it is differentiable and f prime of c, f prime of 0 is equal to 0. That the function, this continuous function may not have an extreme value at c is equal to 0. This example shows it. Okay. But this is this Fermat, even though the converse is not true, this Fermat's theorem is true and important. Here is a concept of critical number. Critical number. If f prime of c is equal to 0, then this number c is called extreme point. Extreme point. Or if f prime of c does not exist, is still this number c is called a critical number. So if f prime of c is equal to 0 or f prime of c does not exist, then the number c is called the critical number. This critical number gives us a starting point to analyze the behavior of the given function. So let's find out the critical point of the given function f of x, x squared plus 16 over x. How? Just to differentiate it, to have this. So let's it be same as 0 and solve it. Then if x is not if x is not equal to 0, then this is always bigger than 0, and this should be 0. So x gotta be 2. So when x is equal to 0, the f prime of x does not exist. And f prime of 2 is equal to 0. So the x is equal to 2, x is equal to 2, and x is equal to 0 are 2 points which that are critical numbers. Okay? So at x is equal to 0, f prime does not exist. At x is equal to 2, f prime of 2 is equal to 0. Okay, so those two numbers are critical point of the given function, x squared plus 16 over x. Okay, then with these observation, we can develop a kind of algorithm to find the absolute maximum and absolute minimum values of a differential function on a closed interval a and b. Okay, here is the answer. Okay, follow the 3 steps. First, find the value of f at the critical point of f. First, okay, if you have a critical point, to find the critical numbers, and then find the value of f at the end point of the interval, and compare the value of the function at those points. Then the smallest, the largest value among those are absolute maximum of the function, and the smallest value of these first 2 steps are the absolute minimum of the differential function f. So if you have a critical numbers, all you have to do is find the value of the function at those critical numbers and the end point, and compare those values, and the largest one is the absolute maximum and smallest one is the absolute minimum of the function on the interval. Okay? And next, f of x, if f of x is looks like this on this interval, then find the absolute maximum and absolute and minimum value of f on the given interval. What you're supposed to do? Okay, you have to find the critical numbers and find the value at that point, and find the value of the function at the end point, like this, here as 5 over 4, and compare all those values, 1, 2, and 5 over 4. So, this 2 is the largest value and 1 is the smallest value. So the maximum, absolute maximum of the function f is 2 and absolute minimum of the function is 1 at x is equal to 1. But nowadays, this is the way that you're supposed to do. But if you can draw the graph, which looks like this, then what you can think? You can think this value and these values are the ones. You can easily see that it has the maximum value as a 2 at x is equal to 0, and you can have the minimum value at x is equal to 1 as 1. So you can, if you can draw the graph and you can magnify or squeezing it to a small size, if you can do so, you can easily deduce the conclusion from the functions. So now you have tools. These are the graphs that I draw with Sage, so you should be able to do so too. Okay. Next is the mean value theorem. Here, this mean value theorem show the following in here. Yeah, we will see how the signs of the first and second derivatives of the function influence the extreme values of f. Okay. Here, okay. So we begin with the Rolle's theorem. Yeah. Let f be a function satisfying these three conditions. F should be continuous on the closed interval, differentiable on an open interval AB, and f of A is equal to f of B. Then we can always tell that there exists a number C such that f prime of C is equal to 0, like this figure 5A. If it's a continuous function on the closed interval, and if differentiable on an open interval AB, and f of A and f of B are same, then it's moving up and down. So we should have a certain point with the horizontal slope, horizontal tangent line, which means f prime of the function at that point is 0. You can have one or many such point. This is the Rolle's theorem says. You should remember the three conditions should be satisfied to use Rolle's theorem. The generalization of Rolle's theorem is the mean value theorem, which this graph shows. This says if function satisfies the following two conditions, not three. Two conditions, then there exists a point, there exists a number C in the interval, in the open interval, such that f prime of C is equal to f of B minus f of A over B minus A, which also can be written in this way. Actually, this is the formula that f of B is equal to f of A plus f prime of C times B minus A, which is delta x. This is the kind of the formula that you have seen in section 3.4. Okay. Anyway, this mean value theorem has this formula, which is shown in this graph. If you have the continuous function on the closed interval and differentiable on the open interval AB, then you can always find the slope of the function. Slope of the function between these 2 points. Oh, it's very hard to draw. Yeah, you can find the slope. Okay. Anyway, I can erase it. Okay. Here you can find the slope between this point and this point. Okay. This is this. Okay. Then you can always, since it's continuous and differentiable, so you should be able to find a point that has the slope which is parallel to the line connecting these 2 points. That's the mean value theorem says. Okay, let's draw then we may define h of x like this, and from here, here, the proof is, this is the proof. This proof can be made from the Rolle's theorem. Yeah. So if you define h of x like this, then it also satisfies the first two conditions of Rolle's theorem, and because h is continuous on the closed interval and differentiable on open interval, and then h of a and also h of a is equal to h of b. So Rolle's theorem says there exists a number c such that h prime of c is equal to 0, which is this. So f prime of c can be written as this. This is the conclusion of the mean value theorem. There exists a c in an open interval AB that satisfies this. So mean value theorem is just a simple corollary of the Rolle's theorem. But this mean value theorem has a lot of important applications. Okay, and that's what you have seen. In general, the mean value theorem says there is a number at which the instantaneous rate of change is equal to the average rate of the change over an interval. Okay, so yeah, there are many examples. The applications of this mean value theorem. You can easily find some movie clips on application of mean value theorem from YouTube and others. Okay, anyway, the extreme value test as a critical number, Okay, here. Increasing and decreasing test. F prime of x, if f prime of x is equal to 0 on an interval, then f is increasing. You know it. And if f prime of x is less than 0 on an interval, then you know f is decreasing. The slope is negative. Then the first derivative test says if c is a critical number at of a function f which is differentiable on some open interval containing c except possibly a c. So c may not c is not the important factor. Okay, here. Okay. If f prime changes from positive to negative at c, then f has a local maximum at c. If f prime changes from negative to positive at c, then f has a local minimum. As you see, if the f prime, the slope is positive. Slope is positive, so it's increasing. But it's from positive. If changes from positive to negative, then definitely we should have a local maximum. If slope changes from the negative, it's decreasing, to the increasing, from the positive, from negative to positive, it changes. Then you see it has a local minimum. So this graph shows what this first derivative test says when f is differentiable. Then we can tell at this critical point, this function has a local maximum or minimum when the sign changes. But if the sign does not change at the critical point, if the sign does not change at the critical point like this, then the signs are all positive in this case, and even at this critical point, when f of x is equal to x cubed, then this f has neither local maximum nor local minimum. So these are the conclusions that you can draw from the changes of the sign of the derivative. Okay? The proofs can be given in simply this, and you can read. This shows one part of the proof. You can do the second and third part as an exercise. Here, find the local minimum and maximum value of this. If you can draw this graph, you can easily see this. Then, what is the local maximum and local minimum in the interval? This is going to be a local maximum, and this is going to be a local minimum. If you find it, then you can easily find it. This part, you don't have the derivative here. You don't have a derivative. Derivative does not exist at those points. So critical, those are the critical numbers. Here, derivative is 0. So it is a critical point. So you have a 3 critical points, and at these 2 critical points you have a local minimum. Here you have a local maximum. You can verify it by checking the first derivatives and then see the change of signs. By the first derivative test, you can say it has a local minimum and local maximum on those 3 points. Second derivative test says this. If C is a critical number such that f prime of C is equal to 0, and f double prime of x does exist in an open interval containing C, then we can have 2 statements. If f double prime of C is bigger than 0, then f has a local minimum. What that means is second derivative is positive. What that means is the slope is increasing. Slope is increasing like this, from negative to positive. So you can expect it has a local minimum. This second derivative is negative. What that means? The slope is decreasing. Slope is decreasing from. Slope is decreasing. So slope is changing from positive to negative. So you can expect it can have the local maximum. Okay. This is what it says. Since f double prime of C is positive, by the increasing and decreasing test, f prime of x is increasing on some open interval containing C. That includes the critical number. So f prime of x is less than f prime of C is equal to 0, and f prime of x is bigger than f prime of C, which is 0 on the interval. What that means, the sign changes from positive to negative to negative to positive. So we can use this first derivative test to get the second derivative. Okay? So by the first derivative test, then you can have the second derivative test. The other examples are the adaptation of the above theorem. Let's see. To find the local minimum and maximum of this function. X cubed minus x, which looks like this. Then how? Local maximum and local minimum. How you do find it? First find the first derivative, and then find the critical numbers, and then find the second derivative and check the change of the signs on the second derivatives. But I may not do it in that way. From the graph. If you draw the graph, you can magnify it. Then you can easily find the critical numbers and local minimum and maximum. This looks like this. So you can easily find the local maximum and minimum by just looking at the graph. Okay. For this example, and if you can draw the graph, then you can find from this the derivative is obtained. Solving the derivative, then you can find the critical numbers like this. I think this should be of Now I make a copy of this command, which is the function of this, and finding the derivative of it. Then we may paste it in here to evaluate the critical number of this given function, and even we can draw the graph of it. Here plot f, and so okay. Okay, so we may just copy those in single cell to plot the graph of the function like this. And then from here we can easily find the local maximum and local minimum from there. We can, and also we can find the, critical points are there, and we can draw the graph to evaluate the value at that point to figure out the local maximum and minimums we did. And for the functions like this, let's draw the graph of this one to check whether our observation was right or not. Okay, x cubed minus x here. Instead of this, we say x cube minus x, and then we can find the we can find the critical values here, and also we can draw the graph to figure out what the local maximum and local minimums are there at the critical values like this. So we can verify what we did with the CAS systems to simulate what we did. Okay, the exercise problems in section 4.1. Here, we were asked to find to determine if the following statement is true or false. So, I gave the solutions on it, so you can check it and you can verify it by Sage or something to draw things in it to submit it. Or you can prove if the statement is false, then all you have to do is giving a counterexample. Just supply a counterexample like this. Or if it is true, then you may have to prove it. There are many ways of proving it, but if you use by the way of the contradiction, then you can easily find the proof of the conclusion that you have. Okay. This is what this method is like this on this. For the continuous function f, and f has only one zero when 1 0. Okay. If f is strictly decreasing, here what we have to do is, for a continuous function, if f is strictly decreasing, we were asked to show it has only 1 0. Then what we supposed to do to prove it is, suppose we have more than 1 zeros when f has a continuous function, then we can easily show it is not strictly decreasing. Okay, so I have explained it a little bit on on one way of proving some mathematical sentence by the way of contradiction. This is the way that that we usually use in many mathematical proofs. And also finding the critical point, all you have to do is just do the computations what you need to do. Okay, here. And draw the graphs and find the derivatives here. So there are many examples and things, finding the local maximum and minimum, and you may draw the graph and what? Here. So you may just copy. Okay, you may just copy it here to find the graph of it. So you can easily find this is a critical point. So since now you have graphing tools, so you can easily many problems. Since it's a critical point, and you can think about the local maximum or minimum. Here, in this case, you have a local minimum here, but local maximum does not exist. So if you can draw the graph, then you can do lots of things. There are many other problems which was proved by hand, but you can also use the SAGE tool to solve it. Okay. I think that will wrap up the problems in section 4.1 here. And these are the inequalities that hold. Here those examples shows how you can use mean value theorems to prove such things. But you can also prove these by what? By the computational tools now without much difficulties. Okay, and also you can even simulate the proof like this. Here, you can draw the graph of those two, both sides, to compare with the inequalities, hold or not. But before, many of things can be proved by mean value theorems like this. And I have given some proof of the Fermat theorem in detail, which comes from Wikipedia, and proof of Rolle's theorem in general, and increasing and decreasing test, and etc. So there are whole information for the section 4.4 in the book, so you may go through it, and if you have any questions, and raise it in the bulletin board, so we can go through it. Okay, I think that end of the section 4.1. Then we will start section 4.2. Any questions before we start section 4.2?